Hello there. We need to discuss some basic concepts in thermodynamics today and some misconceptions and things like that before we get into solving problems in thermodynamics. So, this lecture is going to be mostly about those things. It does show up in problems and contests, it's people want to test if you really have a clear idea of what temperature is and what the difference from between temperature and heat is, what hot and cold mean, things like that. Okay, and sometimes the values is temperature scales that people use and why they use them. And finally, this thing called how do I quantify heat? It's a pretty loaded question. All right. Okay, so first thing, I found that whenever some of my videos get likes on them, maybe they're useful, it gets distributed much more than the ones that have fewer likes. So definitely I will request you to subscribe to this channel, and maybe hit the like button so people can distribute it. And also a lot of these I've written the book and it's in the this physics bootcamp.org. So you may want to check that out. Okay. So temperature versus heat. Let's one by one. So temperature versus heat. So a whole bunch of things I'm going to write down. First, temperature is not heat. Is not. So a whole bunch of misconceptions I'm going to write down. Not number one, not heat. They are two different things. Heat is energy, temperature is not energy. So temperature is not kinetic energy. A lot of students seem to have really big misconceptions of temperature kinetic energy of gas. Not just kinetic energy. It's not kinetic energy of gas. So it's also not any kind of energy. It's not hot, means more temperature. You feel hotter, then it's more temperature. I'll tell you, hotter doesn't mean more temperature. You already know hotter does not mean feeling hotter. Say you go outside. Say you go outside and maybe say cold. Okay, you feel cooler air. Okay, something like that. So it doesn't mean its temperature is lower. Temperature lower. No. Well, you can easily see that say on a still day, no wind, say you have a 0 degree Fahrenheit day outside versus windy day, 0 degree Fahrenheit. Now this feels less cold, this feels less cold than that, but the temperature is same, and the only difference is the wind is blowing more. So the wind is carrying away energy from you, and so it makes you feel cooler, feels colder. So these subjective things do not give us a measure of temperature. Subjective things like that, it can give you a measure of temperature. So if you compare same thing, so you're comparing basically one thing and this is another thing at the same temperature, and that's why you're getting fooled by temperature not giving you a sense of hot and cold. But suppose I had the same so this is H2O, and you're gonna dip your finger in here and see if it's cold, which this also H2O, and they are at the same temperature, then they're going to feel more or less the same. And if this is at T1 and this is at T2, if T1 is more than T2, then T1 will feel harder to touch. But because they're the same system, you can use your sense to actually tell which is hotter, which is cooler, and that is okay. But because these guys are different system, you can't tell. So the whole bunch of things temperature is not, right? So what is temperature? If these are not things that are temperature. And so it's actually a pretty abstract idea, okay? It's kind of almost like what is mass? You may have wondered what is mass. So it's an inherent property, right? And so you have to think about something inherent, some way you can get to it in terms of conceptually, right? So conceptual thing that underpins the idea of temperature is so-called thermal equilibrium. So and just like a conceptual thing that underpins the concept of mass is inertia. So if you don't understand, so inertia itself is a very abstract idea, and I'm not going to go there, but temperature is linked with another abstract idea, and that's why it's very hard to grasp initially for people and to accept it, okay, and use it in their thinking. And that thing is thermal equilibrium. And so I'm going to now describe thermal equilibrium. Let me erase this and get to thermal equilibrium. Okay, thermal equilibrium, and there is a related concept called thermal contact, which we'll talk soon, okay? So thermal equilibrium, what is thermal equilibrium? So you take any object, so this is abstract, so we're gonna do some abstract stuff here. So say take a piece of steel, whatever you take an object here. So this is an object, and you thermally insulate this object. So there are materials which we call it thermal insulators from the rest of the world, and leave it for a long time. Then this object will reach a state after a long time. Object will reach a state so this object is undisturbed object, reach a state that we'll call thermal equilibrium. Now, so this begs the question that this thermal contact, this is insulated. Now, so in order for me to actually do this is like a chicken egg thing. You have to be able to say it doesn't exchange energy with the outside environment. So basically what I'm saying is there is no energy exchange. There is no energy exchange with outside. So that's what this insulated thing is doing. Now here's another, this is also abstract thing, right? Energy exchange, no energy exchange. Okay, so it's this whole idea of thermal equilibrium is tied in with the no energy exchange. So we can actually do another system. Now let's see, this is thermally insulated. Imagine a space that's thermally insulated. So this is kind of an universe unto itself. And now we have object A in here and an object B here. Now there is no energy exchange. There's no energy exchange with outside. This is blocked energy exchange. But these guys can actually exchange energy. Can exchange. Okay, so we'll say they are in some thermal contact. Okay, so that we will say they are in thermal contact. Now you leave it for a long time. Leave for a long time. Then they reach a state of thermal equilibrium. Okay, so what's the big deal? They reach a state of thermal equilibrium. Well, at that point we are going to say they share a property. So A and B are in thermal when A and B are in thermal equilibrium with each other. They have the same value of an intrinsic property, kind of like a Mossad search. This, but we're going to call this property. We will call it temperature. Okay, so that's so temperature is the property an object has when it is in thermal equilibrium. When it's thermal equilibrium itself, it has some temperature which we don't know. We can't compare it with anything else. Over here, both guys are in thermal equilibrium, and they have the same. So I can compare the temperature of A with temperature of B. So we can say temperature of A equals to temperature of B. And here we say it has some value of temperature which we don't know what it is. Okay, it's just some value of temperature. Unless I compare these two systems, I don't know how to get the temperature. And that's how you measure temperature. Measuring temperature is you take one of these things as some kind of standard and compare its temperature to the temperature of that guy. And so now we're going to talk about how do you measure temperature when you have defined temperature this way through a thermal equilibrium. Okay. So what happens is we so we have say we have two systems. We have water, and we put a mercury. We put a thermometer here. Okay, so we have, this is system A and system B. The way we measure temperature of A is we look up the volume of mercury in B. So temperature of A equals to volume as a proxy of mercury in B as a proxy for temperature of B. So basically we're saying temperature of A is equals to temperature of B. And how do I get the temperature of B? We look up the volume. This tells you that temperature can be, we can develop a numerical scale of this conceptual thing called temperature, very abstract thing called temperature, by actually looking at some other property. So the volume of mercury is we find that if I take mercury, some amount of mercury, says suppose m kilogram of mercury, says the volume is V1 at some temperature T1, then same m kilogram mercury volume will be V2 at temperature T2. And you can see that if I have some standard temperatures at which we assign, just pick up some values, say 0 degrees, and this is say 100 degrees. In some, you just pick up randomly some standards which reproducible states. So this can be a reproducible state like ice, water, and maybe vapor, equilibrium. So this is so we have water and ice and vapor over here, and then I put a thermometer here, and it's a reading over here. So reading, let's call it 1, and this is the 1. So the reading at 1, and then I put the same thing in a container in which we have boiling water, and there's a steam, boiling water and steam, and we have same mercury, but 1 is over here and the 2 is over here. So we can assign these are the two volumes. So this was a V1, and now we have a V2, but temperature is T2. And then we can say a change in this volume will correspond to say 100 divisions of some scale, and that is how we define cell scale. So we can say, all right, when the volume is V1 and volume is V2, this temperature will be 0. So this will be my point. Temperature will be temperature of so this mercury is B system, right? Temperature of the B will be 0. When volume is V2, is over here, I'll call that 100. I'll just pick a scale, and that will be a Celsius scale. If I pick it some other values for these guys, that will be some other scale. For instance, if I want to do Fahrenheit scale, I'll call this randomly 32 and call this 212. So from here to here is be 180 divisions. Over here will be 100 divisions. So this will be Fahrenheit scale. And you can already see that if I assume the volume was kind of linear function of this thing temperature, then if I place this over here, the same, and some temperature unknown, and it was over here for TA here, and so this is the volume when temperature is TA, let's call it VA. So I go here and the volume is VA, so I can just read off that temperature. That's the TA. So this is how we actually can get temperatures, and this is how we measure it, and that's how it's related to the thermal equilibrium. Basically what's happened is the water here is in thermal equilibrium with mercury here, and I'm using volume of the mercury as a proxy for the temperature. Okay. Of all this, there are many properties, not just mercury. You can have many properties as proxy for temperature. Of all the proxies that were discovered and invented, you can have magnetism as a proxy. The materials can magnetize, they lose magnetism as the temperature go up. So you can use anything that changes with temperature as a proxy for temperature. You can build a temperature scale, like a resistance of a wire changes with temperature, and you can use the resistance of wire in a thermocouple. So like a myriads of things can serve as a thermometric substance and thermometric property, so as a proxy for temperature. Okay. Of all the things that were discovered, the one that has gas, like a constant volume gas thermometer, played a big role. Okay, and I want to kind of give you a little bit of that now. Okay, so here is a constant volume thermometer. So basically, if you want to know temperature of something, say this is maybe a water or something, then we would dip this in this bulb, and bulb has up connected with this U-tube, and there's a it should be all this blue, should be all blue, so it's connected with this. So what happens is, if you change the temperature, say this system A, so this is some temperature A. I want to know what the temperature A is. This bulb will, the gas here, there's a gas here, will expand and push the mercury, and you will adjust this so that you push back, the pressure gets higher, and you push the mercury back to this same level here. Okay, so the gas's volume remains the same, and then you read up what the pressure that you need to maintain the same volume, and that pressure is a proxy for the temperature. So let's see, I read up different pressures. I have different gases here. So if I do the experiment with nitrogen with known temperatures of these guys and I plot it, it will look like this. As I take out, suppose in how much gas I put, I change. So here what I'm doing is I put, say, nitrogen in there, and different amounts, different quantities. It still fills up the whole thing, but it has a different amount of pressure. So if so we as we lower the pressure inside there, amount of materials less and less, I see the the temperature follows this temperature versus the pressure that I read follows this. But if fill with a different gas, it follows a different pattern, and they all meet at this point. Meaning, if I have this is from here, you can extend it because zero pressure, you'll not see anything. So this is extended to almost empty, okay, which means the gas become ideal gas, low density gas become ideal gas. An ideal gas gives you a unique temperature value. So we have a temperature scale based on ideal gas. Ideal gas behavior, and that's called we usually written capital T, and it's called absolute scale. Also called Kelvin scale, and this is more common in physics. And its relation to other scale is like T in Kelvin scale is 273.16 plus temperature in the Celsius scale. So when temperature 0 degree was freezing, temperature will be this much Kelvin scale. So the values will be different for this scale, but you can see that delta T, if I say in the Kelvin scale, will be this delta T in the temperature. So 1 degree change in Celsius is 1 degree change in Kelvin. So like T2 minus T1 for the 2 bars will be T2 minus T1 in degree Celsius, and this is degree Kelvin. So you got to know this as well as that, or you just know this and then try to use that. Let me you can really read this. This is you should read this more on this. This is very important. Constant volume gas thermometer is very important system. So constant volume gas thermometer. Because it is important in the development of the basic idea of temperature. Okay, so in terms of the relationship between scales, you have there are two standard places often used between 0 and 100. So this is a temperature that we normally encounter in everyday life, and of course there are temperatures which go that direction and temperatures that go that direction. For instance, in the center of the sun, you'll have a 10 to the power 7 Kelvin, and you can go all the way to if you keep going this way, you can all the way to 0 Kelvin, and 0 Kelvin has a theoretical importance. You can go some of you may have a question, can we go below 0 degree Kelvin? And your answer is yes, and you can go negative. They were called negative temperatures, negative Kelvin temperatures. and it has been achieved. What does all mean, etc. You might learn in future courses, but in introductory courses we just say, okay, this is the limit and that's all you're going to do. But that may, you can check it out later. So say we use this scale, these three scales, and a lot of problems you'll encounter, very elementary problems have to do with testing. If you know this stuff, that this is 100 division, 180 division. This will be 100 divisions, not 1800. 100 divisions, 100 divisions, and this is 180 divisions, because this division is made too many compared to that. So this is much more finely divided. So suppose there is some temperature here, and in Celsius it reads C, in Fahrenheit it's F, and Kelvin reads K. So what's the relationship? So C, so equals C minus 0 divided by 100 minus 0 must be equal to F minus 0. This is the slope, is the same line. That's F minus 32 divided by this one is 212. This is also a mistake. 212 minus 0, so that's corresponding. And of course you for C you add 273.16 to get Kelvin, and from there you can get Fahrenheit. So this one can be simplified. You can have a C over 5 is this 32, F minus 32 over 9, or you can say C is 5/9 what happens in F, right, minus 32 over 9. So here you can say delta C is actually 5/9 of delta F. So 1 degree in here is only 5/9 degree, and so this is for the change in temperature, and delta C equals to delta K. So these are two relations. Don't need to remember one relation. From one relation you can find the other, but if you want to remember, often we're gonna do in thermodynamics, often we work with changes. And you say, okay, so here is a problem that you might encounter. Heated to raise Fahrenheit of temperature by 5 degree Fahrenheit. How much was the temperature raised by in Celsius? And a lot of people just say, okay, here is a wrong way to do it. Okay, this problem will be wrong. Will be, okay, 5, I just plug in here, I should say C over 5 equals to 5 minus 32 over 9. And this will be wrong, because it is doing, it is actually saying that it's raised by this. So this is giving me delta F. So I'll be using this, right? So delta C, I want to know how much change by, not exact temperature, by what was the rate, what was the amount of change. So this will be 5/9 of delta F, which will be 5/9 of 5 is going to be 25 over 9 degrees Celsius. So this is a very common mistake, and you got to avoid that if you want to kind of do problems in thermodynamics. Now I see the videos run more than 30 minutes. We are going to talk about quantifying heat in the context of when we do first law of thermodynamics. Okay, so that's the law you have to know before you can actually quantify heat. um, okay, so I think I'm gonna stop here. I know this is a lot of different concepts and conceptions and misconceptions that I tried to address. Hopefully this was helpful, and don't forget to hit the like button. Appreciate that. Okay, thank you. Take care. Bye.